Hey everyone, this is the second section of the nuclear chemistry unit. This is really an extension of the PowerPoint on nuclear energy. It talks about fission and fusion here, so we're going to look at different types of natural and artificial transmutations. This do now question is a review of what we looked at in the past lesson where you had to do equations. So what you have to do here is look up the decay mode on the reference table N and fill it in the first blank, and then mathematically figure out what the missing piece would be. So go ahead and do that and solve for that missing piece. And when you solve this equation, you look up the alpha particle on reference table N. You'd have to look up the atomic number of plutonium on the periodic table, and then you can fill in and see that uranium-235 is the element that would be made. So as a reminder from the last lesson, transmutations are when a radioisotope undergoes a change and emits some sort of rare particle, and it changes into something different. It changes into a different element. So we've already looked at different natural transmutations. These are the ones we did the equations for, so that do now questions an example of a natural transmutation. This is when a nucleus spontaneously decays to form a new element, which means there's no collision involved. The element breaks down on its own. Everything that's on table N can decay naturally. You could write an equation for all of those. An artificial transmutation is when the reaction doesn't happen on its own. An element can be forced to change into another element if you bombard the nucleus of the target with high energy particles. And this will cause them to change. And a piece of equipment called a particle accelerator, which I mentioned last time, speeds up the particles enough to cause an artificial transmutation. And this is how artificial or man-made elements are produced. So this is an example equation for an artificial transmutation. So what would happen here is you would have this nucleus of californium, very creative, guess where they made it, and they would bombard it with a nitrogen nucleus. And when those two things collide, this new element is formed, dubnium, and also 4 neutrons are given off as byproducts. Okay, so you can see the format of an artificial transmutation reaction is different than the format of a natural transmutation because there's two things on the left-hand side that have to collide in order for that new element to form. So how to identify a natural versus artificial transmutation, an artificial transmutation must have 2 reactants, whereas natural transmutations only have 1 because the element decays spontaneously. So if you had to just do an identification, the format would be different. Now, you don't want to say that this is a decomposition reaction because a decomposition reaction is a chemical reaction. You'd have the same elements on both sides, you're just separating them. You have a new element, so look for new symbols, okay, on either case here, but you'd have 2 reactants on the left for an artificial transmutation. Practical applications of artificial transmutations would be nuclear energy, which you already looked at the presentation on. You do need to know that nuclear reactions in general, whether it's natural or artificial, any nuclear reaction is going to yield a ton more energy than any chemical reaction will, okay? Because you have this thing called mass defect. A very small amount of nuclear mass is converted into a lot of energy. This very famous equation shows that relationship. E equals mc squared, where E is energy, m is mass, c is the speed of light. The speed of light is a very big number because light is like super fast and we're squaring it, okay? So if we have even a very tiny amount of mass, even if this is very small, when we multiply it by the speed of light, which is, I think it's 3.1 times 10 to the 9th meters per second, something like that, and square it gives you this enormous amount of energy, okay? The energy yield of any nuclear reaction is about 1 billion times the energy released when the same amount of a fossil fuel like coal, oil, or natural gas is burned. We're going to go over fission and fusion now. So fission is when a nucleus splits after being bombarded. So remember, the word bombard means to hit something really forcefully. Bombarded with a high speed neutron. Okay, so to remember this, fission, split. Okay, a fissure in a rock would be like a crack in a rock, a fissure. I don't know if you did that in earth science. So fissure is like a crack in a rock. So fission is splitting something apart. So this process was really described in the videos that were one of the videos that was embedded in the nuclear energy lesson, that Bill Nye clip. So the basic process here is the nucleus is bombarded with a high-speed neutron, and the nucleus splits. So we have this nucleus, we hit it with a neutron. The nucleus splits into chunks and gives off energy. And it also gives off, in fission, it gives off 3 more neutrons as byproducts. When the nucleus splits, these are going to be more stable than the original, but a lot of times these are still radioactive, and they'll undergo radioactive decay. They'll give off alpha particles or beta particles, or so forth. This is just that animation that Bill Nye kind of showed. Here's a picture from a Regents exam to show you that this is a neutron hitting uranium-235. This can cause a chain reaction. So you do need to know that fission of uranium can cause chain reactions. So when this uranium splits, okay, it splits into smaller elements. Uranium's really big. It splits into 2 smaller nuclei. You don't have to memorize like the process of like what forms, because it could actually be different. But what you do need to know is that uranium splits during fission. These extra neutrons that are given off as byproducts are then available to collide with more uranium, which can then give off more neutrons, which would then collide with more uranium. So it causes this chain reaction. If the chain reaction occurs in a controlled setting, this is a nuclear reactor. So anything like a nuclear power plant, this is what's going on, okay? But the reason it can happen in a controlled setting is because there are these, there's this apparatus called control rods, and the control rods absorb some of the neutrons that are given off and stop them from just like going haywire and colliding with more and more uranium and just keep on like fission, whatever. But if it does go out of control, this is an atomic bomb. Okay, if those neutrons can just keep colliding with additional uranium, that's an atomic bomb. For fusion, fusion is when 2 small nuclei, and it's usually going to be hydrogen and or helium, because those are the smallest elements, unite. So fusion has a U, and so does unite. So when they fuse together, they come together. So here's just examples of fusion reactions. You have these 2 hydrogens turning into heliums. Here you have 2 lighter hydrogens becoming a heavier hydrogen. Here you have 2 hydrogens becoming a helium. Here you have 2 lighter heliums becoming a heavier helium. But as you see, if you see hydrogens or heliums on the reactant side of a nuclear reaction, it's going to be fusion. Just like if you see uranium and a neutron on the left-hand side, it's going to be fission. So to compare and contrast these, just very quickly, fission, fusion, they both are a type of artificial transmutation. They both have a very high energy yield. Fission is splitting, fusion is uniting. Fission, you want to see uranium plus a neutron. Fusion, you want to see hydrogen plus hydrogen, or helium plus helium, or hydrogen plus helium. Fission is nuclear reactor if it's controlled, or atomic bomb. If it's not controlled. Fusion is sun and stars. That's where you get that energy. Also a hydrogen bomb. And where both of them do give off high energy yield, fusion actually yields a lot more energy than fission does. But the reason why they can't use hydrogen fusion reactors is because it gives off so much energy. It's actually really difficult to control the process. So nuclear reactor with uranium fission is easier to control, if you could believe that, than a fusion reaction. But those are basically the differences, the similarities and differences between them. These are two just old Regents questions, very straightforward. Which type of reaction occurs in a nuclear power plant and an atomic bomb? That would be involving uranium, and uranium you're dealing with fission. And what type of reaction occurs in stars such as the sun? That would be fusion. So there's a nice little intro for fission and fusion. Also remember that a natural transmutation, you're going to have one reactant and multiple products, including a new element formed, right? And you'll have either alpha, beta, or positron particle. An artificial transmutation, you're going to have two reactants and a new element and two multiple products. Have a good day.